Hello everyone, my name is Limin. I'm from UC and I'm a PhD student there. Today I'm going to talk about CADE, detecting and explaining concept drift samples for security applications. Let's take a look at a quick example for a multi-class malware classification model. During the training time, we have benign, malware A and B, and you train the classifier. Then during the testing time, if the sample is benign, you can classify it as benign. If the sample is malware A, you can classify it as malware A. However, what if you got a malware C that you never see in the training time? Clearly, assigning them to benign or malware A or B, they are all wrong. This is where concept drift happens. Malware C is a type of drift called unseen family. There's another type of drift called in-class evolution, means that you have some variants in the testing set. Although they have the same label, their feature vectors are quite different from the training data. The bigger difference they have, the more likely they would be misclassified. In this talk, I would focus on the unseen family. You may refer to our paper for the details of in-class evolution. So why concept drift matters? First, new attacks like zero day are not trivial. According to FireEye report last year, they analyzed more than 1 million malware samples every day. About 41% malware families were never seen before. These new families would cause problems. Second, both malware and goodwill evolve over time. In the figure, you can see that their code components are constantly changing during the last decade. And these changes will shift the decision boundary of the classification model, increasing the possibility of misclassification. To give you a real-world example, this is a gradient-boosted decision tree classifier trained on Amber and tested a year later using samples from Blue Hexagon. As you can see, there's a clear decrease on the detection rate, and it's caused by concept drift. To mitigate this problem, we tell the classifier when not to predict. This is an overview of our system. In the production space, we have training data, original classifier, and when a new sample comes in, the classifier can give its prediction. While in the monitoring space, our system CADE has two goals. We need to detect these drifting samples, and after detecting them, we have the explanation module that can find a small subset of important features to explain why this drifting sample is different from the training data. Let's look at what people did in the past. As for the ML community, this has been a hot area since a long time ago, but mostly they require data labeling on the testing set, which is very time-consuming for security applications. A few solutions are from the security community. For example, the Transcend paper. Transcend works like this. Given a classifier and its prediction, they try to assess the classifier's reliability. The reliability is based on how well an input sample fits into existing classes. However, it highly depends on a good definition of dissimilarity and does not scale well. So why it's hard to define a good distance function to differentiate drifting and normal samples? In high-dimensional data, distance can easily lose its effectiveness. To give you an example from the Android malware dataset, here's a t-SNE plot that compresses the original space to a two-dimensional space. In this example, the original space has more than 1,000 dimensions, which is huge. As you can see, the green unseen family here is tangling with the existing families. The distance is not useful here. Another reason is that drifting samples are not labeled. High-dimensional data with label is easy to learn, but these drifting samples are not labeled, making them hard to differentiate from normal samples. Here goes our idea. Since we have no knowledge about drifting samples in the testing set, we may leverage self-supervised learning. Specifically, we use contrastive learning to learn a compressed representation of the training data by forcing the samples in the training set to contrasting with each other. Here's a high-dimensional space where different samples from different classes are dispersed. If we feed them to a contrastive autoencoder, basically an autoencoder with contrastive learning, we can map them to a low-dimensional space called latent space. In this latent space, samples from the same class are tight with each other, while samples from different classes are forced to be far away from each other. In this way, we can learn a good representation of the training data Our assumption is if a sample is far away from any existing family centroids, like the green pentagon here, it's a potential drifting sample. We can apply outlier detection method to detect them and further rank them to find the most suspicious samples for investigation. Now we know how to detect these drifting samples. The next question is how to explain them. The goal here is to identify a small subset of important features that make the drifting sample an outlier. There's a naive solution called boundary-based explanation. We can approximate the decision boundary between drifting and indistribution samples. Then we turn this problem into explaining a supervisor model. For example, Limin, Shep, this has been a well-studied area. Basically, they are using crossing the boundary as a signal to get the explanation. That is to say, what features allow you to cross the decision boundary? Then there are more important features. For example, in the figure, these red pixels allow you to be predicted as a dog, while the green pixels make you a cat. So why this naive solution failed? Basically, we are trying to explain this circle here, perturbing some features of the drifting sample xt. If xt can get into this circle, then we think these features are more important. However, it's hard to achieve this because it's not easy to approximate the decision boundary accurately, given we only have limited drifting samples. Another reason is that it's difficult to drag this drifting sample to cross the decision boundary because it's far away from the boundary in the sparse area. Instead, we propose a distance-based explanation. The high-level idea is we perturb the original features and observe the distance changes in the latent space. Replace this xt feature value with those of a reference sample called xr. The xr is closest to the centroid of nearest family, say A. Then we turn this problem into an optimization problem. We have two goals of optimization. First, we want to minimize the distance between xt and CA. Also, we use Elixir net regularization to minimize the number of selected important features. We evaluate CADE on two datasets. The first one is called driving, a very popular Android malware dataset. We put the unseen family in the testing set only. Another dataset is a network intrusion dataset called IDS. We have a similar setting. For the detection, we compare CADE with two baselines. One is called vanilla autoencoder, another is transient. As you can see, for both datasets, CADE constantly achieves 96% F1 score with fewer investigation efforts compared to the two baselines. We also did a real-world test on a security company, Blue Hexagon PE malware dataset, and CADE is still effective. This raises the question why CADE works. This is the figure I showed before, the t-SNE plot for the original high dimension space, where the green unseen family is mixing with each other. Here's the t-SNE plot for the latent space, learned by the vanilla autoencoder. Still, the green unseen family is tangling with other families. And lastly, this is the t-SNE plot for the latent space learned by our system CADE. As you can see, most of the families are tightened as a cluster and are separated from other families. The green here is mostly far away from existing families. This might explain why CADE works. To verify that CADE indeed provides semantically meaningful explanations, we did some case studies. Here, the drifting sample is from an unseen family called Fake Dog, and its closest family is Ginger Master. The key difference is that Fake Dog usually send SMS to subscribe to premium services. CADE selects the following features as important. The highlighted features are matched with our intuition. For example, send SMS, receive SMS. To clarify, CADE on average selects about 45 features out of more than 1,000 features as important, which is a quite small ratio. To conclude, concept drift is a critical problem for both ML and security applications. And contrastive autoencoder is quite effective to detect such drift. Also, distance-based explanation is more suitable to understand them. Thank you for listening to my talk. Besides, we released a new PE malware dataset, so check it out. Thank you.